Let's look at this inequality. For any positive real numbers a and b, can you see why 8 times the sum of their fourth powers is at least as big as the fourth power of their sum? We'll build up the intuition step by step. We're working with positive real numbers a and b. This keeps everything nice and well-behaved for our proof. Our plan is to start with an undeniable truth and use it to build powerful tools. We start with a simple truth. The square of any real number is non-negative. This is the seed for our chain of inequalities. Expanding this, we get a tool that's surprisingly powerful for bounding expressions. Expanding the square, we see how the cross term fits in. This form will let us relate sums and products. Add 2xy to both sides. Now, the sum of squares is at least twice the product. This is our first bridge. Watch how it connects to our goal. This tool is general. Let's make a clever substitution. Let x equal a squared and y equal b squared. This will help us build up to the fourth powers in our problem. With this substitution, the inequality takes on the same shape, but now with fourth powers. We're building up the left side of our target. Simplifying, we get a lower bound for a to the fourth plus b to the fourth. This is our first anchor for the left side. Let's call it result A. Now, let's create a second tool to handle the right side of the main problem, the quantity a plus b to the fourth. We start with our core tool again, this time with a and b. To get closer to a plus b squared, we need a 2ab term on the same side as a squared and b squared. The trick is to add a squared plus b squared to both sides. This maintains the inequality and sets up a perfect square. Now, let's simplify and rearrange both sides. The left side is combined, and the right side is now ordered to reveal a very familiar pattern. Recognize this? It's the expansion of a plus b squared. This lets us relate the sum of squares to the square of the sum. This is our second key result, result B. It's a bridge connecting a sum of squares to the square of a sum. We will use this bridge twice. Now we'll combine our results in a powerful chain. Applying the substitution, our bridge now connects the sum of fourth powers to the square of the sum of squares. Simplifying, we get the first link in our final chain. Let's put this aside for a moment. Here is the inequality again for clarity before we operate on it. We square both sides. Since both sides are positive, the inequality direction is preserved. Simplifying the powers gives us this. Now we have a connection to the a plus b to the fourth term. To complete our chain, we need to isolate this middle term, a squared plus b squared, all squared. We'll divide by 4. This gives us the second link for our chain. Recall our first link. It says that 2 times a to the fourth plus b to the fourth is greater than or equal to this red term. And our second link says that this same red term is greater than or equal to our target right-hand side, divided by 4. Here's the full chain. We've connected the left side of our problem to the right side through this common middle term. By the transitive property of inequalities, if the first part is bigger than the middle, and the middle is bigger than the end, we can ignore the middle. This gives us a direct comparison between the two main parts of our problem. We are almost home. Multiplying both sides by 4. And there it is. We've built the proof step by step, connecting each inequality visually and logically. QED. Finally, when are the two sides exactly equal? Equality holds when our foundational inequalities are themselves equal to 0. Our entire proof was built on expressions like this being greater than or equal to 0. Equality happens when they are exactly 0, which means the terms inside the square must be equal. For all our steps to be equalities, we need a to equal b. Let's test that. Substituting b with a into the original problem. Simplifying both sides. And we see it holds perfectly. Equality is achieved when a equals b. Thanks for watching. If you enjoyed this, consider subscribing for more math videos.